this laser. So it's a great pleasure to be here at this inaugural conference at the ICTS in Bangalore. I was here for the beginning of it 5 or 6 years ago, and when it had just been approved. And it seems to me very exciting, a very beautiful campus, and I look forward, I hope that this is the first of many talks that I have the honor to give here. So I'm going to be talking about memory, asymptotic symmetries, and soft theorems. And let me start out. This is going to be a slice of work that I've been doing for the last several years with quite a number of collaborators listed here. And these are the people that I've worked with. And also there are a number of other people who have joined in the conversation and made important contributions. So I am going to talk about a triangular equivalence between 3 subjects which have been studied for around a half a century each, and with hundreds to thousands of papers in each subject. And what has been discovered in the last few years is that these 3 subjects are really completely equivalent mathematically. And so there's this triangular relationship between memory, soft theorems, and asymptotic symmetries. Now, there are many copies of this triangle which echo. It's a triangle which governs the infrared behavior of any physical system, or many physical systems. And it echoes throughout all of physics. We could be talking about QED. We could be talking about Yang-Mills theory. We could be talking about gravity. There are leading theorems, subleading soft theorem, sub-subleading soft theorem. There's a classical version of this story, and there's a quantum version of this story where anomalies come in. We could be talking about Minkowski space in any number of dimensions. We could be talking about de Sitter. Anti-de Sitter, I think, is a very different story. There isn't really soft physics in anti-de Sitter space because anti-de Sitter space is a box. And so perhaps this way of viewing things will enable us to understand these other kinds of spaces at the level of depth that we have for anti-de Sitter. We could also be talking about different levels of supersymmetry. In each case, each combination of these things is qualitatively different and interesting for its own reasons. And each one is a talk on its own. In most cases, only one of the 3 corners of the triangle was known. And now that we've found that there is this triangle, once you know one corner, you can get the other 2. And so we're busy tracing out as many triangles as we can. The symmetries in question are infinite dimensional symmetries. And they go along with an infinite number of conserved charges. And these are conserved charges that can and in some cases actually have been measured. And so what are the motivations for this program? Well, of course, we want to understand everything we can about the infrared structure of gauge theory and gravitational theories in the infrared. So just as a problem in mathematical physics, it's a well-posed problem which we would like to fully understand. But I think I'm hopeful that it will have many kinds of applications. I think much of the success of the so-called SCET program, soft collinear effective theory, in organizing the structure of the jets formed at the LHC and understanding that data is related to these symmetries. And in fact, in a recent paper by Duff, Likorsky, and Stewart, they talk about infinite many symmetries, one for each jet. And I believe that these are essentially the same. And so I'm hope that that this will lead to actual improvement in the technology for collider computations. It's also important, I believe, for Minkowski space holography. We certainly need to understand, if we want to study quantum gravity in Minkowski space, what the symmetries are. That's a question, that was the first step in understanding anti-de Sitter space, was identifying the symmetries. And we have not fully understood what the symmetries are for Minkowski space. Now, in the amplitudes problem, there are many miraculous cancellations and miraculous structures that are encountered there. I'm thinking of the n equals 4 program and also the supergravity program. And I believe that many of these are related to these infinitely many symmetries. And finally, this may seem an odd thing because this is a talk about the deep infrared. And this is a string theory conference. And string theory is, to start with, about the deep ultraviolet. But along the way, we run into many structures which are very reminiscent of string theory and suggest a kind of inevitability of string theory. And this is a thought which has come up in many different talks and many different, from many different points of view, that there's an inevitability to the structure of string theory, that it follows from the low energy symmetries of the world. And I hope that this is taking us in that direction. And finally, the triangle has consequences for the black hole information puzzle. And I will show at the end that contrary to popular belief, black holes actually carry an infinite amount of hair. OK, so obviously I can't talk about every triangle or even review every triangle in 30 minutes. And so I've picked out one case. I'm going to talk about gravity. I'm going to talk about the leading soft theorem. The leading soft theorem turns out to be valid quantum mechanically, no anomalies. So my discussion will be valid for both classical and quantum gravity. I'm going to talk about Minkowski space and also about my favorite and most relevant dimension, 4. And I won't have any supersymmetry. And in that case, more specifically, what the triangle is, to put some more words on it, this is just writing over the previous slide, there's something called the gravitational memory effect, sometimes referred to as Christodoulou memory, but it was discovered or first discussed explicitly by Zeldovich and Polnarov in 1974. The other corner of the triangle is the soft graviton theorem, which was written by Weinberg in 1965. And the symmetry that lies at the third corner of this triangle is the so-called Bms supertranslations. It's an infinite dimensional symmetry group which acts on gravitational scattering on the gravitational S matrix in Minkowski space. And the relationships between these three is really very simple. This one is we're going to see is just a Fourier transform. This one is a vacuum-to-vacuum transition. And this one, again, is one is the ward identity of the other. OK, so what I am going to do in the rest of the talk, what time did I start? OK. I just started, right? OK, 9 minutes ago. All right. So what I'm going to do in the rest of the talk is I'm just going to go through the 3 corners of the triangle and give you a sort of cartoon explanation of them. They're all well understood, and then talk about what the connections are along the 3 sides. So first of all, let me review this corner, Weinberg's soft graviton theorem, which was discovered in 1965, and that is if you have an n+1 point scattering amplitude in which one of the external lines is a graviton whose momenta I'll denote Q and has some polarization epsilon mu nu, and you let the momentum goes to 0, that's what soft means, small momentum, that is equal to this funny factor. I've dropped 2 pi's and so on. This funny factor, the polarization tensor contracted with the momenta of the external particle divided by the inner product of the graviton momenta with each of these summed over all the external particles. I'm using a convention here in which ingoing and outgoing particles have opposite signs of p0. This number times this exact same amplitude without the graviton insertion. This, of course, is divergent as q goes to 0. So this is often called the Weinberg Pole. And then, of course, there are corrections of order q to the 0, which we actually recently, they were thought to be non-universal, but recently we've discovered that this term and the next one also have some universal character, which are related to another set of triangles, which I won't have time to discuss. But I'm just going to discuss this one for now. And the derivation of this is actually a very simple diagrammatic derivation. OK, now let me talk about gravitational memory, which is probably less familiar to this audience. So the gravitational memory effect is this. Suppose we, at LIGO, as a gravitational wave passes by, the weights, the distance, the proper distance between them will oscillate. But along with the oscillation, there's a DC effect, which pushes them, a cumulative DC effect, which pushes them further apart. And in other words, we start out with some separation S, some gravity waves pass by, and at the end of the day, they're separated by S plus delta S. Actually, in the case of LIGO, since the weights are hanging on pendula, they'll be restored to their initial position. So ELISA, where we just have satellites, which are inertial detectors orbiting in space, is a better place for measuring gravitational memory. But even so, people have talked about measuring at LIGO if you do it fast enough before the pendulum swings back. And in fact, it doesn't have to be gravity waves going through. It can be any kind of waves which carry energy. Now, how do you calculate that? Well, you use the geodesic deviation equation, which is in every textbook in general relativity. So here, this top line here is the flat Minkowski metric in retarded coordinates. U is retarded time, R is the radius, and then this is just the metric on the two-sphere. This is the flat Minkowski metric. If you have a gravitational wave, you have subleading corrections. And the subleading corrections are often denoted in this way. I'm using a complex coordinate z for the sphere at infinity. And so this is a perturbation of the metric, which is transverse to the direction of propagation of the wave. I'm imagining that these gravity waves are produced very far away, and these detectors are effectively at infinity. And this term represents gravity waves quite, almost, but not exactly. The reason it's not exactly is that this metric turns out to be exactly flat to this order if this CZZ, this metric component, is the second derivative of a function. So CZZ doesn't have to be 0 in flat space. And if you write down the geodesic deviation equation, you solve it, you find that the change in the separation between the two inertial detectors is proportional to the change in this CZZ. So CZZ doesn't have to be 0. It will change. So this is a DC effect. There's a lot of discussion about measuring gravitational memory. There was a recent discussion of measuring it in the pulsar timing arrays. It's a good thing because you look at them every few weeks. So it's hard to see an AC effect. But if you come back a few weeks later and things are shifted a little bit. So the problem of measuring gravitational memory is quite different and requires different kinds of experiments and detectors than gravitational waves. But it's quite plausible that it will be measured in the coming decades. OK, so what is the relationship between gravitational memory and gravitational soft theorem? Well, I've pulled out here two equations, one from Weinberg's seminal paper in 1965, and one from Thorne and Brzezinski, who were looking for experimental signatures of gravitational waves, of gravitational memory in 1987. And in fact, if you look at it, it's incredibly similar. So Brzezinski and Thorne set Newton's constant to 1. And both of these are formulas for the change in the metric. You can see that they're essentially exactly the same formulation. They almost use the same notation, except that Thorne used K and Weinberg used Q. But they're computing different things here. Thorne is computing the change in this perturbation of the metric, what I was calling the change in CZZ at late and early times, while Weinberg was computing the pole in the scattering amplitudes. So to see that these things are in fact exactly equal, these two papers that were written, I guess, more than 2 decades apart, you have to use the fact that a step function, which is what Thorne and Brzezinski are looking at, is the Fourier transform of a pole. Now, I think it's a very beautiful thing that, and shows the universality of this formula, that Weinberg wrote down this formula while thinking about scattering elementary particles. Thorne and Brzezinski were scattering black holes and stars, but still, it's exactly the same formula because we're going into the deep infrared. So the relationship between gravitational memory and the soft graviton theorem is just a Fourier transform. Now, I like gravitational memory because one of the things that's always bothered me of this discussion of soft gravitons is how do you measure a soft graviton? You measure things of a definite energy in an accelerator, but it sounds a little bit unphysical to measure a soft graviton. But what you do is you measure its Fourier transform. You measure the pole. You measure the change in something. And Brzezinski and Thorne explained to us down to the last detail actual experiments that would measure the Weinberg pole. OK, so I gave this corner, and the relation. Now let me write the third corner, which is the so-called Bms symmetry. So Bms, in 1962, set out to show that the Poincare group could be recovered as a symmetry of general relativity in asymptotically flat spacetimes. But they failed. There's no sense in which the Poincare group is a symmetry of general relativity in asymptotically flat spacetimes. You are required, there's no canonical Poincare subgroup. You're required to have this infinite dimensional group, a much bigger group called the Bms group, which has infinitely many Poincare subgroups. And in particular, it has one way of thinking of this is that the spheres that live out in infinity are out of causal contact with one another, and they become ultralocal. And you can have something called super translations, in which a time translation would move the sphere at null infinity uniformly up and down. But the super translations, of which there are infinitely many, allow you to move different points on the sphere at different rates. When you do this, the metric does not take the form I wrote on the previous slide with CZZ equals 0. You change this subleading, you leave it flat, it's a diffeomorphism, but you change this subleading piece, you shift it by the second derivative of this function f, which represents how fast you're super translating along each point along the sphere. And so that means that this CZZ is the Goldstone boson of spontaneously broken supertranslation invariance. So supertranslations do not leave the standard metric with CZZ equals 0 invariant. They map it to another metric, which is a different physical configuration. It has the same energy, but for example, it has different angular momentum. Now, what is the relationship? So now I've got the third point on the triangle, but I've got two more connectors that I have to flesh out. Well, I'm doing this on one slide here. You can work out, so it's a symmetry. It acts on this BMS, they gave a symmetry. It changes, it acts on the Hilbert space, it moves particles around, and it also, importantly, if you work it out, creates soft gravitons. And so you can write down an operator which creates soft gravitons, which generates supertranslations. And you can show, being careful about the structure, there's some really thorny subtleties about the structure of spatial infinity, but once you sort them out, you find that this operator commutes with the S matrix. Now, if you have this as an operator identity, you can take its matrix element in any state. So it gives you, given any amplitude, you can get a relationship to another amplitude. And after quite a bit of algebra, you can show that that relationship is Weinberg's soft graviton theorem. To say that in one sentence, Weinberg's soft graviton theorem is the Ward identity of the symmetry discovered several years earlier by BMS. And of course, whenever you have a symmetry, there's a conservation law. And the conservation law in general relativity is that the energy radiated in at any given angle is equal to the total accumulated over all time at any given incoming angle is equal to the energy radiated out at the opposing angle in the future. And one can check that that is true. OK, so finally, we just have this last leg of the triangle. How do we go directly? So we know that BMS symmetry must be related to gravitational memory because they're both equivalent to the soft theorem. So how do we understand their relationship directly? Well, you find there's a formula that, suppose you have just flat space, and then you throw some energy through it. You disturb it. You excite it. After you do that, space will be flat again, but there's no reason it should return for a generic passage of energy or radiation. There's no reason it should return to the same flat metric. And in general, the previous flat metric will differ from, the initial one will differ from the final one by a BMS transformation. So we worked out what the formula for that BMS transformation is. This is all classical relativity. And we can write what this formula is. And you find something very beautiful. Of what happens is this. A BMS transformation is a diffeomorphism, of course, but it's a large one, which we should regard as non-trivial. And if you have the sphere, if you take the sphere at null infinity and you tile it with detectors, and then you send a wave out carrying any kind of energy, when you come back, the relative positions of all those detectors will have been changed. And they will be different distances, there will be different angles. The relative positions will all have been changed, and they will have been changed exactly by the BMS transformation. So any pulse of energy can be thought of as a domain wall, which enables a transformation from one BMS vacua to another. Now, what does this have to do with black holes? Well, black holes carry infinite hair, BMS hair. So we would not say that a stationary black hole and a boosted black hole are the same thing. They have different energy, they have different momenta. But that boost is just one element of the BMS group. And things which differ by any element of the BMS group are inequivalent. They carry different quantum numbers. Now, The no-Hair theorem, of course, is a theorem, and it says that any two stationary black holes are related by diffeomorphisms. But those diffeomorphisms, in general, can be BMS transformations, so that doesn't mean that all black holes are equivalent. In fact, there are infinitely many black holes which all carry the same mass, but different angular momentum. Now, we're used to the fact that energy conservation in some way, which we don't understand in great detail, constrains outgoing Hawking radiation. Everybody believes that the energy and momentum of the final state is equal to the energy and momentum of the initial state. But according to this discussion, there are an infinite number of conservation laws which constrain Hawking radiation. And moreover, at the end of the day, the zero energy vacuum has an infinite degeneracy. Part of the argument is at the end the black hole is gone and the vacuum is restored to some unique state. There can't be any imprint of the energy left there. And that argument is, at the very least, needs some modification. So the conclusion then is that the infrared structure of gauge and gravitational theories is richer than we had previously appreciated, and that there's a lot that we need to understand. Thank you.
Are there any questions, comments? Sunil?
Yeah, in the past you've argued that one should consider an extension of the BMS group by the infinite Virasoro rotations of this sphere. So I didn't understand, did those play a role in this triangle or somehow?
Well, those things are associated with, those have a triangle of their own.
Mm-hmm.
So, those have a triangle of their own. So there was a conjecture by Barnick and Trissart and Banks, and also a beautiful paper by De Boer and Salutkin that I only discovered very recently, which said much of this a long time ago, that the asymptotic symmetry group, BMS, the Lorentz transformations act on the sphere at infinity like the conformal group. But we're used to the idea that once you have the global conformal group, it's usual for the global conformal group, it wants to get enhanced to the infinite dimensional group. And in fact, if you look at the original argument by BMS, it's not clear. They just demanded by fiat that those transformations be everywhere finite and infinity. And so it's a very natural to conjecture that BMS, the SL2C in BMS, should really be the infinite dimensional conformal group. And there had been some discussion of this. And looking at this triangle, we realized that if that was true, there had to be a soft theorem. And Freddie Cacciazzo and I showed that there was indeed a soft theorem. That's how we discovered the subleading soft theorem. So this is a different triangle. So we found the subleading soft theorem, which has some anomalies which we haven't understood, but at least at the classical level, there's a subleading soft theorem. And then there's the third corner of that triangle, which predicted that there has to be a new kind of gravitational memory, which has a chirality to it. And indeed, Sabrina Pistersky and Sasha Jabodov and I showed that, in fact, there is a new kind of gravitational memory that has a chirality to it, but doesn't seem likely that it's going to be hard to measure, but it's certainly there theoretically. So that's one of the other triangles. And that's a triangle where all three sides have been, and corners have been found, but it's not true for every triangle on the board that all three corners are known.
Are there any other questions? If not, let's thank Andy again. Wait. So it may have occurred to you that this is the last section of this meeting. After I close the meeting, Spenta will say a few words. But before I close the section, I would like to ask the organizers to all come to the front. I know there were quite a number of them. Where's Justin? So in view of the time, I will already start talking. I'm sure that I talk on behalf of all of you, that this has been a great meeting. We have had great talks. We also had a very nice atmosphere, good weather. Everything that was in Spenta's power and his assistance was done. They also set a record. I think this is the Strings meeting which has the largest number of locations. and that is not a simple thing, because in Bangalore, with the Bangalore traffic, and given the distances, that requires an enormous logistics. And these organizers have managed to do that together with their very professional staff. And I think we should give them a round of applause. And then I close the section. Now the floor is yours.